matrix from 1 to 0 for transformation from frame 1 to frame 0. So the frame 1 was in red over here, and we had frame 0 which was in black. And you could see that the origins were not coinciding with each other. They were separated from each other. And we used a very simple method. We constructed this transformation matrix. We had the R matrix here, and we had the position of the origin of the frame 1 with respect to 0 over here. Okay, and we could operate this transformation. So the remaining elements were 0, 0, 0, 1, and we could operate this transform on this augmented vector RF with respect to 1 expressed in the frame 1. And when you see this point F from the frame 1, that's the red frame, you could see that the coordinates were 3, 0, 0. And when you took the product of this, you got 4, 0, 2, and 1 was of course here. And you could see that you are able to get the relationship of a position vector in different frames. You can determine the position vector of a point as observed in different frames. You can relate them using this transform. In this, in the next part, we discussed a little complicated case, a little more involved case, where we had the frame 3 slightly tilted with respect to frame 0, and we began constructing it. We could construct the first 2 columns, and then we said that the third column is obtained by just taking the cross product of the first 2 columns in this order, I cross j. But now comes the issue of how do we obtain this third column using matrix methods. So in order to explain this, although we are on this problem, we take this opportunity to introduce you, if you do not know already, and we will introduce you to the cross product in the matrix form in this lecture. Let's take a fresh page. Now suppose we have a vector with in the 3-dimensional space. Let's say we have the vector A, and it has components AX, AY, and AZ. We are considering only one frame at the moment. So these are the elements of this vector. This is vector A. We also write this, we assume that AX, AY, AZ are real elements, and we write this in this fashion. A is the vector A is an element of R, the real space, and because this is a 3×1 matrix, we can write it like this, or we can also write it just as R3. Okay. In the same way, let us also take a B vector. Here we have Bx, By, and Bz. And here also we have this notation, that is the B vector is also composed of real elements. So it's an element of R 3×1. Okay. So it just says that these elements they are in the form of a 3×1 matrix, and these elements are real in the real space. So if you take we are already familiar that if we are interested in the dot product, uh, the other way in which we represent this vector using ijk notation, which you are quite familiar with, is that we write it as axi, the unit vector I, plus ay, the unit vector j, az, unit vector k. And likewise, we also write um, b vector in the same way. So this is bx I plus by j plus bz. Okay. This is the way we represent it in matrix form, and this is how we represent it using the unit vectors I, j, k. Essentially, it means that the component that is being multiplied by the I direction is ax. This is the component multiplied by the j direction, and this is component multiplied by the k direction. So here uh, we have already seen now that if we want to work out the dot product of this matrix, dot product of A and B. So we have the dot product, which we also call as a scalar product or scalar product. We write it as A. Conventionally, we write it as A dot B. Okay, when we represent it in the form of ijk. But in matrix form, we also write this as A transpose B. And you can see that because it is a scalar, A transpose B, A transpose is a 1 by 3 because this is a 3 by 1. This is also a 3 by 1. So here you have 1 by 3 operating on a 3 by 1. Okay. So this is a 1 by 3 because it's a transpose of a 3 by 1. And this is a 3 by 1. And you know that the outcome of this is a 1 by 1, which is a scalar. And you know that the transpose of this scalar also is the same thing. So you can also write this as B transpose A. Okay. So it's the same thing. It's a scalar. Now, what about the cross product? So this was for the dot product. We know that this is actually a scalar. Now, what about the cross product? That means, suppose we are interested in A cross B. Okay. This we know is a 3 by 1 because we know that A cross B is a vector and this is actually a 3 by 1. Okay. Now, can we have B, can we have a transform which operates on the vector B? Okay, this is a vector, so we can represent it as a 3 by 1. So this is a 3 by 1. Can we operate something on this? Can we have a matrix here? And what should be the order of this matrix? If we multiply this matrix on B, we should be able to get A cross B. Okay. So what should be the order of this matrix? Can you tell me?
3 cross 3.
It should be 3 cross 3. Okay. And we will designate this matrix as A cross. A cross. So this A cross is a 3 by 3 matrix. Okay. We'll show it like this. Now, what are the elements? We will discuss it out shortly. Conventionally, what we do is we write these two things together and we determine the, so A cross B is actually written is obtained like this. You are already familiar with it. So here we write I, we use the method of determinants. So I, J, and K here. And here we have AX, AY, AZ, and this is BX, BX, BY, and BZ, and we take the determinant. So this determinant gives us, so I, we multiply with I. So here we have AY, BZ, AY, BZ, minus AZ, BY, minus AZ, BY. Okay. So this is going to be multiplied with I. The second one, I'm going to write it below. That is minus, because we have minus j here. We'll have minus j and AXBZ minus AZBX. So this is going to be multiplied by j. Okay. And then we have plus k. K I'll write later on. Here we have AXBY minus AYBX. This is multiplied. So this is our vector product. We know that this is how we obtain the product. Now, if we write this in terms of a matrix, okay, if we keep the B matrix here, let's say Bx, as we have done here, Bx, By, and Bz. Okay, so we keep the B matrix here and determine what are the components that are needed for this part here. Okay, so sorry. We try to fill up these elements here. Let's also, okay, I think you can straight away write this. So let's see. Now, AY into BZ, that means AY into BZ. So I'll fill up AY here. AY minus AZ into BY. BY is here. So this will become minus AZ. Okay. And over here, what should come?
0.
0 into bx minus az into by plus ay into bz. Okay, so this gives us our first row. The second one is minus ax bz. So here we will have minus ax into bz, then plus az bx. So this will be plus az into bx. What will come here? 0. So you have az into bx minus ax into bz. Okay, this part. And the third one is likewise ax by. So here it will be ax into by minus ay into bx. So this will be minus ay into b, ay into bx, and sorry. So here you will have 0. So you can see it is minus ay bx plus ax by plus 0. Now you have got a matrix here. It's a matrix which is a 3 by 3 matrix, and you can see that the components of this matrix are obtained from the elements of the vector A, elements of the vector A here. So these components are just obtained from there. If you look at this matrix, this is our A cross matrix. Okay, so this is our A cross matrix. A cross matrix. If you look at the structure of this matrix, you will see that the diagonal elements are 0 and the off diagonal elements are anti-symmetric. See, there's minus az here, there's az here, there's ay here, minus ay here, minus ax here, ax here. Okay, so one thing is absolutely clear, that it is a skew symmetric matrix. Okay, so A cross is a skew symmetric matrix. And you can see that if you take the transpose of this matrix, this row will become a column here, this row will become a column, and you will get the negative of this. So you will see that if you take A cross transpose, it is equal to the negative of A cross. Okay, this is the property of skew symmetric matrices. So any cross matrix obtained from a vector, a 3 by 1 vector, any cross matrix is a skew symmetric matrix. Okay, so we'll write this as a cross matrix, and it is obtained from the elements of the vector itself. Okay, so this is how it is constructed. So now we are in a position, of course, let's analyze this a little further. We saw here that A cross B is equal to A cross, structure of which is like this, operating on B. And so this is actually A cross B. This is a skew symmetric matrix, and we know that A cross B is actually equal to minus B cross A. Okay, so you can see for yourself that it can also be written as minus B cross A. Okay, so A cross B can also be, the order can be inverted, and you can see that minus B cross A. The order can be reversed, right? So this is about the cross product, which we had not discussed earlier in our lecture. So this is the cross product in matrix form. Okay. Perhaps some of you must have been aware of this, but for those who have not done it before, I hope you have got the point clear. Okay. So it's always the A cross matrix is always a skew symmetric matrix, and it operates on this, and you can get the cross product. Now coming back to our example over here, if we look at this example, we are to take the cross product I cross J. So we have I here, we have J here, we have to take I cross J. Okay, so it's very simple. So let us construct, uh, we can write the K vector, K3 expressed in the frame 0 as I3 expressed in the frame 0 cross J3. And now you know what is this cross product, how it can be obtained in matrix form. Okay, so this is equal to, this is I. So we can construct its cross matrix, right? So what is its cross matrix? We'll have it in the skew symmetric form. So 0, then we'll have 0 here and 0 here. Here you have minus the Z component, that is, this is the Z component of I, because we are constructing an I cross. So we'll have to consider the first column, right? So this is minus of the Z component. That means 1 by root 5. Here you have the Y component, which is 0. And here you have the minus X component. Minus X component is minus 2 by root 5. Okay. So you can automatically fill these up by making them skew symmetric. This will become minus 1 by root 5. This will be 0. And this will be 2 by root 5. So these are the elements of the A cross. So this is the A cross matrix, that is I cross matrix. Okay. And we have J. J is 0, minus 1, 0. So 0, minus 1, 0. So when you operate this I cross J, you will get K, K3 expressed in the frame 0. That is 0 into 0 minus 1 upon root 5 into 1. So here you will get minus 1 upon root 5 plus 0. Here you get 0, 0, 0. So this part is 0. And here you get 0 minus 2 by root 5, 0. So this is our third column, which is K. All that you have to do now is write this third column here. So you get 1 minus 1 by root 5. This is 0 and this is minus 2 by. So what you have got here is the R matrix. This is needed in order to construct the T matrix. So we have got this part now. We are interested, we also need the position vector of the frame 3 as observed and expressed in the frame 0. So what is the position vector of frame 3? It's over here, right? So it is 0 units along the x direction. It is 3 units along y direction and 2 units along z direction. So we can write this as, so we have the R matrix here, but we are interested in the T matrix. So let's construct the T matrix. Write it here. So T3 to 0 is equal to, so we have the R matrix. R matrix is 2 by root 5, 0 minus 1 by root 5. Just a second. Then we have 0 minus 1, 0. We have minus 1 by root 5, 0 minus 2 by root 5. So this is the R portion, this portion, okay? Then we have 3 zeros here, 0, 0, 0. Then we need the origin of the frame 3. Frame 3 origin is here, that is no units along the x direction when seen from frame 0. It's 3 units along the y direction and 2 units along the z direction, and this is 1. So we have constructed the T matrix. So this is our T matrix, and you can see for yourself that it's very easy. Now, there are certain checks which you should certainly employ while you do this construction. So here we have the origin. So this part is our R. Okay, and we have one column here. So So we have this structure here. This is corresponding to the origin of the position vector representing the origin, and this is just 3 by 1 here, 1 by 3 here. So this is the structure of this matrix, and this is T3 to 0. So I hope now you have understood how the construction is done, and you can handle even more complicated cases. I hope this is clear to all of you. Anybody having any difficulty, you can ask me. Please go ahead.
Sir, how the x coordinate comes 0, sir?
Yes, please.
How the x coordinate comes 0, sir, in the x3 format, three third frame?
How the x coordinate?
In third frame x coordinate 0 कैसे आ गया सर?
0, 3, 2.
Yes sir, मैं इसमें 0 कैसे आया? I don't understand.
You see, this frame 3 is this blue frame. Okay.
Yes sir.
Its origin is lying at H.
Yes sir.
When the observer in frame 0, he sees this origin of frame 3 from here.
Yes sir.
What does he see it as? He sees it as a vector like this.
Yes
I
sir.
am not on that vector, but it will be this vector from here to here. Got it?
Yes sir.
So what are the components of that vector? You see, it is this vector. This vector. What are the components of this vector? When seen from frame 0, 0 units along the x direction. You see this, it's on this face itself.
Yes sir, understand sir.
So
Okay.
0 units along x direction. How many units along y direction? 1, 2, 3.
2. Yes sir.
And how many units along z direction?
2
1,
units.
2. Okay.
Yes.
So
Yes
this
sir.
is a simple way
Yes
of
sir.
obtaining
Yes sir,
components. I
got it
hope.
sir. Got it.
Okay. Okay. Any other question that you have, please don't hesitate to ask so that we are able to proceed smoothly to the next.
Hello, sir.
Yes, please go
Sir,
ahead.
please repeat how we get I3 dot I naught
I3?
dot I naught.
I3 is over here.
Yes, sir.
Oh, this component.
Yes, sir. Yes, sir.
You see, I3 is here and I naught is this vector, right? I naught. So you take this vector parallel to I naught, you place it here. You get this vector here. So you have two vectors, I3 and I naught. Okay, got it?
Yes,
So
sir.
when you take their dot product, what do you get?
Cos theta.
Cos theta, sir.
You this is I3, this is I naught. Yeah, so you will get cos theta because magnitude of I3, magnitude of I naught multiplied by cos of the angle. Now, what is the cos of this angle? Oh, sorry, it is adjacent. It's not opposite. It's cos, isn't it? Cos is adjacent divided by hypotenuse. I'm sorry. It is adjacent side divided by hypotenuse. Adjacent side is how many units? 4 units. So it's 4 units here divided by the hypotenuse. Hypotenuse is how much? 2 square plus 4 square, square root of that. So this becomes 4 divided by square root of 20. That is 2 root 5. Got it?
Got it, sir.
Yeah. Okay. Any other query?
Sir,
Yes.
sir, we are finding these transformations to just locate the points on the links. If we are considering with respect to some definite frame.
It's not just see, these transformations are useful because if we know the position vector of a point in one of these frames, and if we know the position of that frame with respect to another frame and the orientation of that frame with respect to another frame, okay, then we can determine the position vector of that point with respect to the other frame.
Yes,
This transformation, just multiply this transform on it, and you will be able to get the position vector in that other frame.
yes, sir.
Is it?
Yes, sir.
Yeah.
There is a possibility that we may find a space where this matrix is null or and is giving an invalid result. Sir, maybe the link, maybe the space which we are finding is not valid in this region.
No, I did not get your question exactly what you mean. You're talking of a null matrix. What I did not understand.
Sir, sir, in that book, J.J. Craig book, sir, I read that in the uh, in that aeroplanes, when we use a turret gun to fire, then we have only the 2 degrees of freedom, the up and down and the rotation one. So there is a possibility that we may not able to rotate it somewhere other in the other space. So there the degree of freedom will be constrained in the two directions only. So that's why I'm asking that whether this matrix will give
I
some
think you are confusing with the singularity with the singularity, but that will come a little later. We will have a discussion on that, but you need not confuse yourself with that at the moment.
okay, sir.
I hope, yeah. As far as what we have discussed, is it clear to you or not?
Yes, sir. Yes, sir.
Yeah, yeah. So the care that you should take is when you construct this T matrix, you should check whether this matrix is satisfying the properties of the R matrix. The satisfying the properties of the R matrix means its columns should have the magnitude of this column should be 1, each of these columns, okay? And secondly, they are mutually perpendicular to each other. And here you see the magnitude. So none of these elements in this R matrix will be more than 1 in magnitude, okay? Here, this is the position vector of the origin of the frame 3 with respect to frame 0 expressed in frame 0. And so here you may have higher magnitudes, no problem. Okay. But here in this part, you will have it has to satisfy the properties of the R matrix. You can also invert it, and now that you know how to invert it, you can employ this particular technique. So you already have R. If you want to invert this matrix, you can construct its inverse by just taking the transpose of this. So this part just becomes a transpose of this. And here, this column over here, it becomes minus R transpose the position vector of the frame 3 with respect to 0, this. Okay, so this minus this transpose this, that will form the origin of this. So, and the other elements will remain the same, 0, 0, 0, 1 will remain the same, and you will get the inverse. Okay, so you can see it is really very, very easy. You can construct the inverse so easily. Okay. You don't have to do row and column operations in order to obtain the inverse. Only you have to perform this matrix multiplication. Of course, you have to take the transpose of this matrix and operate that on this vector. Any other query that you have? Okay, since you don't have any more doubts, we will conclude our lecture here for today. So we'll discuss the Dennavit-Hartenberg convention, and before that, we will discuss some more aspects of the transformation matrix. So thank you for now. We are going to end our lecture. Have a nice day.